So today we will continue with equality constraint optimization. And what we have seen in the previous lecture was the so-called elimination method, which allowed us to solve an optimization problem where we want to minimize certain objective function. This objective function is a function of n variables, and its value is a scalar. And we have several equality constraints because we have these functions h here, which map the n-dimensional Euclidean space to an m-dimensional Euclidean space, which basically means we have m equality constraints. And we would like to find the optimal values of the decision variables such that the objective function is minimized and these constraints here are satisfied. And what we have seen in the previous lecture was how to use the elimination method to basically get rid of the inequalities, basically eliminate them and replace them by some other optimization variables. And then what we have done was to convert this equality constrained optimization problem into an unconstrained optimization problem in new variables. And then that unconstrained problem we can solve using arbitrary method. It can be an analytical method, it can be some numerical methods, for instance gradient-based or gradient-free methods. And then once we have obtained the unconstrained solutions, we still have to do to recover the solution of the original problem. So we had some substitution at the beginning, and once we solve the unconstrained problem, we take the solution, we plug it back into the substitution to get the solution to the original problem. And these elimination methods we have seen that they can be applied when the constraints are linear. Then it's rather easy to eliminate those constraints because you can easily compute the null space of the constraints and then use the parametric representation of equality constraints. And today we will cover a more general method, which is called the Lagrange method, which allows us to solve the problem in the case that we have nonlinear constraints, and also in the case where we cannot directly solve the unconstrained problem analytically, like when the function here, for instance, is nonlinear. And these kind of equality constraint optimization problems, they occur very frequently in practice. So when you go to a company which, for instance, has to ship some products from the starting node to the final node via some intermediate nodes. Okay? And the objective that we want to achieve here is that we know how many products enter the beginning of the network. We know that at the end of the network we have to ship the same amount of products, so there are no losses here. And the objective here is to determine how many or which quantities should be shipped along respective routes which are connecting these nodes. Okay? So these kind of problems, they appear, for instance, when shipping oil or gas. So essentially here, these nodes represent some pumps which move the gas or the oil forward. But they can also appear, for instance, in mail delivery. So you have some mail entering the post office and it has to be delivered here. And we are free to essentially separate the mail into separate transportation routes. Okay? You can think about shipping with trucks, whatever. Okay? So these kind of optimal network flow problems, they appear very frequently in practice. And they fit perfectly into the framework of equality constraint optimization. Why? Well, as we said, the same amount which enters the network must also leave the network, which means there is no accumulation in the nodes. So how can we write that there is no accumulation in node number A? Which constraints, but also, okay, let's start with the node S. How do we make sure that there is no accumulation here? Accumulation meaning either new products are added or somebody is stealing from the node. Yeah.
Xs is equal to X1.
So it's the well-known principle that the sum of the incoming flows must be equal to the sum of the outgoing flows. Okay. So that's for the node S. Then for node A, that's even easier. That's just x1 is equal to x5. Okay, and we continue further and we essentially write the mass balance or the mass conservation balance for each of these nodes here. Okay, so that's exactly what we do here. And then we say that at the end of the network we have to ship the same amount which was also here. And now we would like to find the optimal allocation of flows, and usually in these kind of networks, each of these channels or paths, it has different cost associated with it. Okay? This cost can be, for instance, directly be proportional to the length of the path which is connecting two nodes. Okay? But the bottom line is for each path we have some price C, which says how much are we going to pay if we ship this amount of products using the i's paths here. And obviously we would like to minimize the cost while satisfying these constraints. And this is exactly what equality constraint optimization in practice is about. And then what we can do very easily is to convert these constraints into that compact representation, AX is equal to B. And then we can use, for instance, the null space method to eliminate these constraints and convert the problem into an unconstrained optimization problem and solve it very easily. Okay, so this is just like an example of a real-world case where equality constrained optimization is used. And then you can do fancy stuff. For instance, this particular solution where I have assumed that the price of delivery through corresponding channels is proportional to the square of the quantity which is being shipped. Okay? And squares are frequently used because they essentially represent energy which is required to push the oil, gas, or whatever through a pipe as a function of the shipping quantity. And then this is the optimal solution, and as you can see, all constraints here are respected, meaning what enters also leaves the node, and the sum everywhere is equal to 1. The sum here is equal to the incoming node, and these are the outgoing, and at the end, we also ship 100. And then you can play with a problem like this. What, for instance, if this pipeline here is broken and nothing can be shipped through? How can we adjust the optimization problem to reflect this requirement? There are two ways. One is kind of more involved, and the other one is easier. How can we modify the problem? So essentially what we are saying is x2 goes away. So that's option number one. What we can do is we can modify these constraints, and whenever we have x2, we just remove the corresponding part, right? So we remove it from here, then we simply say what enters the starting node must also leave through x1. Okay? But then we also leave out essentially, it is no longer that easy. I mean, what is the mass balance with respect to B? What was the, okay, so it was x1, x2, this was x4, x3, okay? So we are here.
So x3 is equal to x4 in the next case.
Right, which is the same as putting a 0 here and leaving the rest, okay? And the remaining nodes, they remain the same. Okay? So that's option number one, to modify these constraints. There is also another option how to achieve the same goal.
X2 is equal to 0.
Yeah, we can add an additional constraint which achieves the same goal, because both here as well as here we essentially wanted to enforce that x2 is equal to 0. So it is important to also know how to modify an existing problem and to adjust it to a new situation. Okay, then this is how it is done in Prezi. And then when we solve this modified problem, then This is the result. Okay? What we can notice is that now this path here is minus 25, which essentially means that the products are moving in the opposite direction. Okay? So notice that while here we had solution which was all non-negative, nowhere did we say that the solution must be non-negative. Okay? It was just a consequence of the problem being stated that we start with a positive flow and we want to end up with a positive flow, and the path or the network was set up in such a way which allowed only positive flows. But here, now once we remove essentially, or when we set x2, once we set x2 equal to 0, then we actually, to even satisfy the constraints, we do require negative flows. Okay. So here you see a real example of using an equality constraint optimization procedure. Okay, so let us now move to the actual content of today's lecture, which is about the Lagrange method. This gentleman here is Joseph Louis Lagrange. Actually, he was Italian, so it was Giuseppe Luigi Lagrange. He was an 18th century mathematician, actually one of the most famous mathematicians in the history. And one of his contributions was in the field of optimization. And he came up with something which is really an elegant way of solving optimization problems. Probably you have heard about something which is called the Lagrangian. Lagrangian is kind of an extended value function where we also include constraints in the objective function, and then we solve an unconstrained problem. And to illustrate that, let me consider seemingly silly example. I mean, if you look at this, can you tell me what is the optimal solution? It's 1, right? I mean, we have one optimization variable and we are immediately fixing it to 1, okay? So there is nothing to be optimized. But actually, it allows us to show how the Lagrange method works. So what Mr. Lagrange essentially did was, he said, can we maybe solve this problem as an unconstrained optimization problem? Well, we cannot immediately because we have the constraint, so we kind of have to get rid of the constraint. So what he said was, let us move this constraint, I mean, this is just so-called standard form of an equality constraint where we have a 0 at the right-hand side and everything else is on the left-hand side. So when somebody asks you to put a constraint to a standard form, this is what you can do. Again, this is what will be on the next exam. Okay? So you will be given a constraint and you will be asked to put it in a standard form because this is such a frequent task, and all these methods, they require that the constraints are in the standard form. Okay. So, first what Mr. Lagrange did was he transformed the constraint into the standard form, and then what he said was, well, let's put this term here, just the left-hand side of the constraints, into the objective function and treat it essentially as some kind of a penalty of not satisfying the constraints. Okay? So what he said was, I can solve the problem by essentially assuming that I will be penalizing heavily x for not satisfying the constraint. And then this is how that can be achieved. So we have the original objective function plus to that original objective function, we include the left-hand side of the standard form of the constraints, and we multiply essentially this residual by mi, and this mi is called the Lagrange multiplier. And this mi here serves as a penalty of x not being at 1. So essentially what we have done was that we have removed the constraint and we have placed it into the objective function, and we have multiplied the constraint by some multiplier. And now you can see really what has happened? We started with an equality constraint problem, and we ended up with an unconstrained problem. However, we don't know what is the correct value of mean here. We have to find it such that we find the optimal solution of this problem. But this problem is an unconstrained problem, right? So we can actually solve for optimal x and optimal mean here. Okay? So this extended function is called the Lagrangian of the original optimization problem. Okay? And now let me show you what happens if we don't use correct means. Okay? So let me assume that I set mean equal to 0. Essentially, I'm only solving the problem minimize x squared, right? The optimum trivial is here at x equal to 0, right? When I set mean equal to -1, for instance, then the minimum is here, okay? We know that the true minimum of our original problem is at x equal to 1, because that's what our equality constraint said, right? That x equal to 1 is the optimum regardless of the choice of the objective function. But the point here is that if we choose a correct value of mean, and this is again an incorrect value because we see that the optimum is here, okay? It is not there where we want it. However, if we choose mean equal to -2, a remarkable thing happens. The optimum of this problem, of the unconstrained problem, with a correct value of mean, is the same as the optimum of the constrained problem. Okay? So basically we see that this is again kind of a parabola, and the minimum is exactly at the optimum of the original problem. So the idea of the Lagrange method when solving equality constraint problems is first to form this Lagrangian. To do that, we first need to convert the constraints into a standard form. Then we take the left-hand side of the constraints, we place them into the objective function, multiply by some Lagrange multiplier, and then we need to determine the correct value of the Lagrange multiplier, such that the optimal solution of this problem is the same as the optimal solution here. That's the general idea. And here, this is just a demonstration that there is a hope that it will even work. Okay? But nobody will do it in this way, that he will now try like plotting the value function for various values of means. There must be a way how to obtain the correct value of mean. And actually, this is very easy. All we need to do is to solve this optimization problem with respect to x and with respect to mean. How can we obtain x and mean which minimize the Lagrange? So we use the analytical method for unconstrained optimization, right? That's one option. What we can also do is we could use numerical methods, and we will come to that at the end of the lecture. Okay? So how can we solve this problem analytically? So tell me. So we have the so-called Lagrangian, we denote it by capital L. It's a function of x and mean, both are optimization variables. Here the Lagrangian is the original value function plus the Lagrange multiplier times the left-hand side of the constraints in the standard form. What now? Okay, so what is the gradient of L? First of all, what will be the dimension of the gradient? How many optimization variables do we have?
2 times 2.
2 by 1, okay?
So 2 by 1.
So what is the essentially, okay, let me put it this way. The gradient is the partial derivative of the Lagrangian with respect to x, and the second term is the derivative with respect to mean. Okay? So what is the derivative of the Lagrangian with respect to x?
2x
Plus mean. Okay. What is the derivative with respect to mean? X minus 1. Okay. What needs to hold in optimum for this gradient? Greater or equal? Equal to 0. Right? So we essentially ended up with two equations in two unknowns, and we can easily solve them. So what is the optimal solution here? So, x star is equal to 1, and mi star minus 2, okay? Which is exactly what we have achieved graphically. Okay? So at the optimum, the gradient has to vanish, it has to be equal to 0, and from that we obtain these two values. Cool. And we have the solution. This is how the Lagrange method works. And using this method, we can solve pretty much an arbitrary optimization problem with arbitrary constraints. Because here, we no longer require that these constraints here are linear. They can also be pretty much anything. Okay? So this is then what happens, and this is kind of the Lagrange function where I have put mi equal to minus 1. Okay? So again, the main argument here is that the optimum of this problem is the same as the optimum of this problem. While this one is unconstrained, that can be solved easily. This one is constrained and cannot be solved that easily. What is the price we are paying here? So essentially what we said is, we started with a more complicated problem because we had equality constraints. We ended up in an easy problem, which is an unconstrained problem. But there is no free large.
But it's of higher dimension.
Yeah, we have one additional optimization variable which was not in here, right? So that's the price we are paying. But we are willing to pay the price because this problem is so much simpler to solve than this one.
Even for large scale problem.
Even for very large scale.
Let's say 100,000.
100,000, yeah, definitely. Using gradient or the Newton method, yeah, definitely. So let me put the Lagrange method in more technical terms. The Lagrange method is a way of solving equality constraint optimization problems where we have some objective function to be minimized and we have a total of m equality constraints. And then to use the Lagrange method, we first have to form the Lagrangian. The Lagrangian is a function of the original optimization variables plus the function of Lagrange multipliers, where to each of these single equality constraints we attach a separate Lagrange multiplier. And then the Lagrangian is given as the original cost function plus mi1 times this function, mi2 times that one, up to mi(n) times this function here. So that's what this sum here does. So if somebody asks you, give me the Lagrangian of a problem, so we can give a quick example. So if I have minimized f of x, subject to I don't know, x1 plus x2 is equal to 1, and x2 plus x4 is equal to minus 2, how would the Lagrangian look like here? How many variables will it be a function of? So x, of course, because it has to be the function of the original optimization variables, and then as many Lagrange multipliers as there are single constraints. Right? And the Lagrangian is the original cost function plus, now, before we start forming the Lagrangian, we have to convert the constraints into a standard form. Notice that we always have the 0 on the right-hand side. Otherwise, the method does not work. Okay, so we have to first convert it, so I will use the whiteboard. This would be minus 1 is equal to 0, and here it would be plus 2 is equal to 0. Right? And then we simply add this, add the first left-hand side multiplied by the first Lagrange multiplier, and then comes the second one. So this is the Lagrangian. And clearly, for the Lagrangian to be minimized, the gradient of the Lagrangian has to be equal to 0. And there are different ways how to now recover the optimal solution from this system of equations. If if this gradient of the Lagrangian is linear, we can directly solve a system of linear equations. If the gradient is non-linear, then we can use the gradient-based methods or maybe the Newton method. Sometimes we don't even know the gradient explicitly, and then we can use gradient-free methods like those randomized methods. Okay, so those Lucia-Cola, simulated annealing, extremum seeking, they can also be adjusted to work with equality constraints. It's just that instead of the original function, we would minimize the Lagrangian instead. Okay? If the gradient is linear.
The gradient is linear, we can solve it by just a system of linear
Yeah.
equation. But what if we have n optimized variable plus n constraints, and number of rows will be.
But I mean, the gradient of L will be also with respect to these variables. So we essentially the gradient of the function is not the gradient of the Lagrangian. The gradient of the Lagrangian will have more rows.
So every time.
We also increase the size of the system of equations that we need to solve. So let me give you a particular example. Let us assume that we would like to minimize this quadratic function in the 2D Euclidean space, and we have a linear equality constraint. And this example we have already seen in the previous lecture, and we have seen how to use the null space method to basically eliminate this constraint, or there is one more way how to solve it, not using the null space method. What was the name of the method which we have applied here? Okay, elimination, right? What was the principle of the elimination? Was to express one of these variables from this constraint, substitute it, obtain an unconstrained problem using fewer variables, solve that one, and then back substitution into the constraint to recover the other variables. So either the elimination method or the null space method is or counts as a part of the elimination method. Okay? So basically, what we are looking for is the minimum of that function where the optimum point can only lie on this line segment here. And we know that the optimum is here, okay, because we are trying to minimize, and these are the contour lines of the objective function. How would the Lagrange method solve this problem? So what would be step number one? Right. So first we convert the problem into a standard form. How would it be? So we just need to get rid of the 6 on the right hand side and put it to the left. So that's 2x1 plus 4x2 minus 6 is equal to 0. Okay. How would now the Lagrangian look like? How many Lagrange multipliers do we have? Just one, so that's just me. And the Lagrangian is the original cost function plus the Lagrange multiplier times the left-hand side of the constraint. Okay. Now, what would be the gradient of the Lagrangian? How many equations would we have in the gradient? Why 3? Oh, okay. 3 in the sense that x itself is x1 and x2. Yeah, I agree. Yeah. Okay. So we would have something like this. So we would have the partial derivative of the Lagrangian with respect to x1, then with respect to x2, and then with respect to me. Okay. So what is the value of this gradient here? What is the derivative with respect to x1? So we have x1 there, so the derivative of this term is just 4x1. The derivative of this one with respect to x1 is 0. Then we have me times 2 times x1, 2 times me, and here we don't have x1, so that's just 0. With respect to x2, 8x2 plus 4 me. And with respect to me, actually here you don't have much to do because the derivative is just the constraint itself. So qx1 plus 4x2 minus 6. Okay. And we know that at the optimum, so when we put stars here, then this must be equal to 0. Okay. It's well, technically speaking, it is necessary to put those stars because the gradient is only equal to 0 at the optimum and nowhere else, but not necessarily somewhere else. So now we have how many variables? We have 3 variables. We have 3 constraints or equalities, which are moreover linear. So now we can solve for x1 star, x2 star, and e star. So what would be the solution? I mean, it's such a simple system that we can do it by hand. You have to eliminate one of them, right?
So let's say x1 is 0.5. Me? Minus.
Minus what?
1
Okay.
and if you put it into the second,
Can't we also express x2 as a function of me? So that would be what? Also minus 0.5 times me? Now we substitute it there, so that's minus 2 times 0.5 times me, minus 4 times 0.5 times me, now minus 6 must be equal to 0, right? So that's just me minus me minus 2 me, minus 6 is equal to 0, that means that minus 3 me is equal to 6, that's me is equal to a minus 2, right? Well, I should have put everywhere star. And then we recover what is x1 and what is x2. Okay? So that's how this method then works. So this is then the optimal solution. And if you remember from the previous lecture, that was exactly the same solution that we have found using the elimination method. So really these two approaches are identical. Okay? It's just that this one is far more general. Essentially we just need to make the gradient of the Lagrangian, put it equal to 0, and solve that system of equations using our favorite way. Another example, like this one. This is far more tricky because the objective function, I mean, it's nonlinear. I mean, it's convex here. Sorry, this function is concave, but we are maximizing that concave function. So these are again the contour lines, and this is the constraint. That's the optimal point. And we would like to solve this problem. Okay? So what we do is, we form the Lagrangian by adding also the equality constraint. We make the gradient, and we solve the gradient. Okay? Now note that the gradient is no longer linear in the decision variables. Okay? Because x here and y, they enter in a non-linear fashion. But this is such a simple system that we can easily solve them. Right? Again, using just substitution. Express, for instance, x as a function of me, and then plug it in here, and from that we will find out this solution. Okay. So note that the Lagrange method returns not only the optimal solution of the original problem, but it also returns this Lagrange multiplier. And this Lagrange multiplier has some very nice interpretation, especially in economics optimization problems. So let me give you an example of that interpretation. Let us assume the following problem that we are facing. We are running a company, and that company needs to produce heat, either for production or to supply people with heat. And essentially, it can get the heat from 3 sources, coal, gas, and oil. Each of them has certain price here, and each of them has some heating power which is generated by burning 1 unit of a particular source. And each unit of the source also has some volume that needs to be stored. So now the factory has some hard equality constraints which says we would like to purchase particular amounts of these three heat sources such that the total heating power is exactly equal to 200 of the heating units, and the total volume is exactly equal to 100 volumetric units. And of course, if we are looking for an optimal mix of these three energy sources, which first of all satisfy these two equality constraints, and the price of the purchase price is of course minimized. So this is an equality constraint optimization problem. Before we solve it, we first need to formulate the problem. When formulating the problem, we first need to know what are the decision variables, how many of them are there, and what do they represent. So what are your suggestions? What are we going to optimize?
Three quantities of coal, gas, and oil.
Precisely. What will they represent physically?
Physically,
Can be either the
some quantities
like mass or the actually it would be something like a mass because we have the volume. So this is essentially the proportional to the density of the material. Okay, so we are going to purchase masses of individual variables. So what will then be the objective function? If we denote x1, that would be coal, x2 would be gas, and x3 would be water. How would then the objective function look like?
Minimize price.
So A times x1, that's the total price of the coal, plus 15x2 plus 20x3. Right. Something like this. Okay. What about the constraints? How can we drive it down?
1.5x1
1.5x1 plus 2.1 x2 plus 2.8 x3. That must be
minus
well, yeah, we could put it in a standard form immediately or afterwards. So the only point is that we have to pick up the correct number. And here we have 4.5 x1 plus x2 plus 1.3 x3 is equal to 100. Right? So that's the problem. I guess one thing that I didn't say here is that we are actually going to assume that the price is proportional to the square of the purchased amount of the heating media. And that's again kind of natural in practice because larger amounts they usually require higher transportation costs. Okay, so whenever you are transporting something through pipelines or via trains or something like that, we usually assume that the price is proportional to the square of the shipped quantity. There is also a mathematical kind of motivation why we want to use squares here, because we know that we are going to take the derivatives, and if there wouldn't be a square, then essentially the variables would disappear from the equations, and we need to keep them. Okay, so there is both kind of practical as well as a theoretical motivation for using the squares.
The square of optimized variable?
Yeah.
The square of the cost.
It's up to us. For the cost, it's actually important to know the relation or the fraction between individual costs. That's far more important than particular values. Okay? And now we would like to solve this problem. So what is the Lagrangian? Before doing that, as was already mentioned here, we need to put these constraints into a standard form. Okay? So that's always the first step. And then before the Lagrangian, but actually, okay, I want to show something more general here. This problem is one of the most frequently used problems in the war. It's called the quadratic programming problem. in quadratic programming, what we have is we have a quadratic cost function and we have linear constraints. And actually, we can write this problem in far more general form like this. So we have cost function in which we have the quadratic term, we have a linear term, and we have a constant. And all equality constraints, they are put together into this compact representation. Now, what is the relation between this general form and this particular example? When asking for the relation, we have to answer what is capital P, Q, R, A, and B such that it represents this problem. So can somebody tell me what is the value of the matrix P here? So basically, our vector x is composed of x1, x2, and x3. Okay? The matrix P has to be a square matrix because it is multiplying the transpose of x and the x itself. Okay, so it has to have 3 rows and 3 columns for this multiplication to be valid. Okay? So in our case, we start by transposing the vector x, that's this one. Then comes the matrix P, which has 3 rows and 3 columns, and that's multiplied by the vector x. Then we have the vector Q transpose. It multiplies vector x, that means it has to be a vector of compatible size, meaning 1 row and 3 columns. And then there is R that we need to determine. Okay? And basically, this, the expansion of this one has to be equal to a times x1 squared plus 15 times x2 squared plus 20 times x3 squared. So we can start from the very end. Do we have a constant term here? Like a constant which is not multiplying x1, x2, x3? No. That means R is equal to 0. Do we have linear terms here, linear in x1, x2, and x3? No, we don't. That means also the Q, this Q transpose, the Q is also a 0 vector. But what about the matrix P? After the expansion, it has to yield exactly these 3 components. So
on the diagonal.
So the diagonal here, because this is the term which multiplies x1 times this one times x1, which is a times x1 squared. Okay? This is the term which multiplies x2 squared, so that's 15. Here it's 20. What about the other elements? They are all 0 because, for instance, this one is which one? x1, x2, right? And there is nothing x1 times x2 here. Okay, so that's why we have 0s here. Okay? So this is the conversion of a particular problem, particular objective function, into this far more general form. Okay? So that's with respect to the cost function. What about the constraints? What should be the matrix A? Again, we are looking for the matrix A such that when we multiply it by the vector x1, x2, x3, we obtain exactly the right-hand side. So we can start with the right-hand sides. So here we have 200 and 100. Okay? So we have 2 equality constraints. What is the multiplier of x1 in the first constraint? So we are here. That's the multiplier, 1.5. The multiplier of x2 in the first constraint is 2.1, and the multiplier of x3 is 2.8. And the same for the second one, 4.5, 1, and 1.2. Okay? So then this one is A, and this one is B. Okay? And this is B. So that's what we do to actually convert the problem into this form. Now, why we are doing that? Because this is a very general form and we can derive the condition for optimality here. This is an equality constrained optimization problem. So we can solve it using the Lagrange method. How can we do? We need to form the Lagrangian of that symbolic problem. What is the Lagrangian? That's the original cost function. Plus. And yeah, if you remember, I will show it here. It was this one. Okay, notice this sum here. So that sum we can actually write more compactly as me transpose times ax minus b. This ax minus b, that's again the standard form of these constraints here. And what this me transpose does is essentially equal to the sum. Okay? So we take me1 times the first row here, plus me2 times the second row, and so on. So this is just a vector form of that sum. How can we find now the value of x and me which minimizes the Lagrangian? So what is the gradient of L is a function of x and b? How many equations? Well, two principal equations, because we are taking the partial derivative with respect to x and the partial derivative with respect to b. So what is the partial derivative with respect to x? And I guess you remember the basic rules, right? So if we have something like z transpose az, and we want to make the derivative with respect to z, that's 2a in a very special case. In a more general case, it's like this. It's a plus a transpose. The other basic rule was that the partial derivative of a times z with respect to z is what? That's a transpose, great, thank you, and z transpose a by z is just a, right? Okay, so why are you saying it is 2p?
When the A matrix is symmetric.
A matrix here, which of course has nothing to do with this A matrix, it's just like general vocabulary, but yeah. Okay? So if this matrix here would be symmetric, then this would be 2a. Okay? And actually, yeah, there is one more property, and we can see it here. This matrix is symmetric. Okay? So that's why the derivative of this term with respect to x is just 2p. The derivative of q transpose x is derivative of this term with respect to x.
Q.
That's just q. Derivative of r with respect to x. That's 0. Derivative of, and here this can be expanded, this part, that's me transpose ax minus me transpose b. So what is the derivative of me transpose ax with respect to x?
A transpose.
Right, so it's here, so we are essentially in